Today I'm gonna show you the definition of stocks. You can see we shall use a logarithm model for continuous time stock price process, x of t. The logarithm model is an advantage for the type of analysis that we will do later. And you need to remember that our use of this kind of model doesn't imply a preference for logarithm utility. And in fact, the utility function doesn't matter in stochastic portfolio. So let's see the definition. The n is a positive integer, and the stock price process x of t is a process that satisfies this stochastic differential equation for any t belongs to from 0 to infinity. And this w is a Brownian motion. The gamma is measurable, adapted, and satisfied this condition. That is because when we try to integrate it, we need this condition hold so that our integral will be meaningful, unless it's meaningless actually. And the this Kc need to satisfy these three conditions. And let's see why is that later. So according to the definition, it can be integrated directly with this form. Log x of t, actually it equals to log x of 0 plus from 0 to t. So gamma, maybe you can use s, ds, plus 0 to t, the sum of Kc s dws. So here, the positive constant x of 0 represent the initial value of the stock. So we can rewrite it as the exponential form. The stock price process can be expressed as here. X of t equals to the initial value times e to the this form. For t belongs to 0 to infinity. And frequently, a stock price process will be referred to simply as a stock. So in our definition here, definition 1, the x of t represents the price of the stock at time t, and it follows from the second one, the second definition, that x of t must be more than 0 for all t, because this term is more than 0, this term is more than 0. So when initial value times an exponential form, so the result is more than 0. And since we assume that each company has a single share of stock outstanding, the x of t also represents the total capitalization of the company at the time t. So in our definition 1, the process gamma of t is called the growth rate. Here, growth rate. And the other term, the Kc v represent the sensitive of x, and we can call it the volatility processes. Volatility. It represents the sensitive of x of t to the number v source of uncertainty. The uncertainty, we know that it comes from it can be denoted by the Brownian motion, right? So we shall see that the first condition of C is similar to the gamma, and second one ensures that the volatility of the stock doesn't rise so quickly as to render meaningless the stock's growth rate. And the growth rate is the terminology from the logarithm model. I mean, in classical portfolio theory, the standard model will use the rate of return. They use rate of return, which I can introduce later. And although the rate of return is used in classical theory, the growth rate is actually a better indicator of long-term stock behavior than the rate of return. So we will prove that in later video. So another thing need to mention is that normally we will use a finite time domain, like t belongs to maybe from 0 to a certain moment t. That is because the finite time domain is commonly used in mathematical finance. That is because we need to use the Girsanov theorem most of the time. But since we do not depend on this theorem in stochastic portfolio theory, all our results hold for from 0 to infinity. And unless we want to set some non-asymptotic conditions here. So let's move on. So it's clear from this definition 1 that the log of x of t is a continuous semi-martingale, because the first term here is a bounded variation component, and the other one, this term, is a local martingale component. So by Ito's rule, let's rewrite the x of t as the e to the log of x of t. That's obvious, right? But if we applied Ito's rule to it, we get dx of t equals to x of t times d log x of t, and plus 1 over 2 times x of t d. Here actually it's a quadratic variation, if you remember the notation we use in the introduction here. But it's actually equals to this term equals to the sum of C v square dt here of t. So when we consider the definition, and we will get a new stochastic differential equation that the x is also a continuous semi-martingale, that dxt over x of t is equals to gamma t plus 1 over 2 here dt plus this one it's simple here. It just put the definition here into this term, and we will get a new, and then put the x of t into the left of this equation. So we will get a new stochastic differential equation. And this is also a continuous semi-martingale. And here, if you remember the definition of the rate of return rather than the growth rate, you can see the growth rate plus this form is the rate of return. And maybe we can denote it as alpha of t. So alpha of t equals to gamma of t times 1/2 and the sum of c of t squared. Here we have the standard model for a stock price process in this term. The dx of t over x of t can be interpreted as the instantaneous return on x of t. So in the same sense, d log of x of t can be interpreted as the geometric return on x of t. We use the language of classical portfolio theory. So I think that is enough for the definition of stocks. In the next video, I will introduce the definition of market and the portfolio. So thank you for listening and see you next time.